Hello, everyone. This is Alfredo Abate, your current Chicago Oracle Users Group president. Welcome to today's webinar. As an attendee, you'll be in listen-only mode. You can ask questions in the chat window, which we will monitor. All questions will be answered at the end of the presentation. We'll also be streaming live on our YouTube channel, and the recording will be available there to view shortly after the presentation is finished. It's great to be here with you today virtually. For those that are new to the Chicago Oracle Users Group, we welcome you. Traditionally, our group meets between 4 to 6 times per year in various locations around the Chicagoland suburbs for presentations as well as hands-on workshops by Oracle experts, ACEs, and authors. With the restrictions in place due to COVID, we decided to go virtual to continue to deliver awesome technical content to our members. Today is our 17th webinar in a series of 20 that we'll be holding until November 18th. We're down to just 3 more after today, so make sure to visit our website and register for those remaining ones. Our website address is in front of you. It's just coug.us. Our user group runs completely unfunded. Our members don't pay any dues, and our meetings have always been free. I'd like to take a moment to thank our sponsor, OAPS.NET Partners, for providing the Zoom webinar platform. They are an Oracle Gold partner and systems integrator with the specialties in areas of financial business solutions based on Oracle applications, both on premises and in the cloud. They provide services in the areas of AP automation, Apex development, database upgrades, and administration. Next week, don't miss our webinar with Oracle ACE Director, Michelle Hardwick, and Assistant Director of Business Analytics, Leonel Nieto, on our dashboarding tool of choice is Apex. You can come and hear about how they built an Apex dashboard for their 3,000 plus faculty members at the Salt Lake Community College. You can register for that one on our website right now. Today, we welcome Kim Berg Hansen, all the way from Denmark, Oracle ACE Director and author. Hi, Kim.
Hi, Alfredo.
Welcome.
And hi, everybody.
Give you control of my screen there.
All right. Then I'm going to switch here. And hopefully you can now see the first slide of the Analytic views, the virtual cube.
We can see it. Thank you.
And I thank you for the introduction. And I can follow up a bit on that if this thing will. Just briefly that I've been working with SQL and PL/SQL since 2000. I have the gold spade, or ACE Director, as Alfredo said, and something that I figure the most important, I'm the quiz master for SQL on the Oracle Developer Gym. If you haven't played with it, I can definitely recommend going there to brush up your knowledge on SQL, PL/SQL, and database design. Alfredo said I was an author, and I've written this book that came out in February. There's quite a bit of examples in there. As said in the ACE program, there's a link here to see more about the ACE program and nominate people if you think they should be there. I work for Trevadis, a company from Switzerland that's also in other countries, including Denmark. So, onto the agenda for this talk. We are going to talk about analytic views, or as I like to call them, the virtual cube. It's a new feature that came in version 12.2. So, okay, it's been out for some years now, but relatively new. And I'm going to explain what it is and syntax, how you set it up, and some other things about the analytic views. So diving into the concepts, what is it? Well, it's like a view, just dimensional. So here, you know, a normal regular view. You have your relational tables, and then you create a view, and that's basically just a query. So that's just some metadata that then represents these relational tables and views, represent them as other relational data, which you can then query with SQL, just as if they were tables, and get some reports in the end. When we are talking analytic views, same thing, we have some relational tables. We have some metadata on it, but what they represent is not transformed relational data, but dimensional. So they look like a cube. Even though they look like a cube, it's still SQL that you can query them with, albeit some expanded SQL, or you can access them with the OLEDB driver for OLAP. So you access them with tools as if they were cubes. No matter if it's a normal view or analytic views, it's virtual. They don't store data as such. The data stays in the relational tables. We can also compare it to a dimensional OLAP cube. For those, we still start with the relational tables, but we copy some data into a data warehouse, and then we build a cube copying the data once more, and then we query it with some MDX or different other tools. With the analytic views, same as I showed before, we can query them using SQL. They look like a cube, but it is just virtual. We are not copying all the data. When we query them, it'll be transformed into SQL that queries the base relational tables. So the anatomy of the analytic view, these new object types, well, we do have our normal relational tables where some of them we use for dimension tables and some of them for facts. And to put that together, we need 3 different metadata object types. The attribute dimensions, we define those on our dimension tables. And then we have hierarchies, which we define on the attribute dimensions. And lastly, we define the analytic view themselves, which is the definition of the relationships between the dimensions and the fact tables, definitions of what hierarchies are relevant in this analytic view, and then definitions of all the measures and calculations and aggregations you can get out of this analytic view. And when we have all of these 3 defined, we can then query using the SQL. And SQL we all know and love, so that's so nice that way. Quick note, if you're using application containers in 12.2 or newer, there's the share with clause that's also available for these object types. And that allows you, for example, to say that you have defined some attribute dimensions and hierarchies as shared across application containers. Also analytic views you might have shared across application containers, but they can be shared either just as the metadata or sharing the objects, both metadata and data. So that you could share like a time dimension, you share both the metadata and data, but a customer dimension, you share only the metadata, so that there'll be different data in each application container. Diving into each of these three object types, metadata object types, the attribute dimension is based on a regular table with dimension values in it, or you can have multiple tables denormalized. You join together with view or materialized view, and I'll show you how you do that. So take a pretty simple denormalized dimension table, items, where the items are the primary keys. The category, in this case, is put in the table. Very often it would be like a foreign key to another table, as I'll show you an example of later. When I have this regular table, I simply do create or replace attribute dimension and give it a name using my table name. And then I define, okay, which columns should be attributes of my dimension. I could give them aliases here. I'm just using the regular column names. And then I need to define levels. So I'm saying I have an item level, I have a category level, and then all attribute dimensions will have the all level. And I specify what's the key of each of these levels, what's the member name. If I want to, I specify what's the order by, that it should by default use when ordering these, ordering data by the dimension. Then I specify also for the levels that if I know an item, it determines category ID. An item can only have one category ID. So if I know an item, I will also implicitly know the category ID, not vice versa. So this is information that the attribute dimension needs to know. I can have branched levels in an attribute dimension. Say, for example, I have a customer dimension table. Now I have normalized tables. The customer lives in a state, and the customer is member of a customer group. And the state is situated in a country. So these are normal tables with some foreign key references between them. The foreign key references are not necessary to do this analytic view stuff, but it's of course good for the optimizer to know such things. Having these, I create, let me get rid of that ink. I create a view which simply denormalizes my normalized dimension tables, joining them together. This view I could then create as a materialized view if I want. It doesn't have to be. Using my view or materialized view, I create attribute dimension, custom attribute dimension with all of the attributes in them, and create my 4 levels here, plus of course the all. And in this case, the level customer, it determines the customer group and the state. The state determines the country. Now, of course, customer therefore also implicitly determines the country. I don't have to specify that myself, it's intelligent enough to understand that it's implicitly determined. I've used dimension type standard for these examples so far. There's another dimension type called time. And the dimension type time, well, is for time dimensions. So here I have created a table to contain all dates that I want to use, with some month, quarter, year, month of year, that's the number 1 to 12, and season in it. So I populate this with some data, all those dates that I'm interested in. Yeah, I could populate this years into the future if I want. And populate all of the IDs and names of months and quarters and so on. Decide that month 12 and 1 and 2 are to be winter, and so on. And when I have that table created, I make an attribute dimension, date attribute dimension. The difference here is I'm using dimension type time instead of dimension type standard. I could, and you'll see other examples out there that use dimension type standard also for these time dimensions. The idea, as far as I'm aware, is that these time dimensions are useful for time series analysis. And as such, I don't think there's any SQL functions yet that use them, but there probably will be. But tools that connect to this via the OLEDB provider for OLAP will be aware of such things. Again, I have different levels here with the determinants that show, okay, the connection between the different levels. But I also have this level type days, level type months, etc. You'll notice I have a level type quarters here. I also have a level type quarters down here. How can that be? Well, the level type tells it how many of these are there in a year. So level type quarters means it's the level of which 4 members exist per year. And that's true both for quarter, Q1, Q2, Q3, but also for season, winter, summer, spring, fall. So both of them are level type quarters. So I've now created a set of attribute dimensions. That's the first object type. Second is hierarchy. The hierarchy also is simply metadata. And what it does is it defines parent-child relations of the different levels of the dimension. And you can have multiple hierarchies for one dimension. But what it also is that it is actually a row source. You can do a select from a hierarchy. You cannot do that from attribute dimension. And that row source has some generated virtual columns and rows that are very much those you are going to use when you query and work with the analytic views. So for example, we had this attribute dimension that's repeat of what I showed before. And then I can create a hierarchy, item category hierarchy, using the attribute dimension. Simply states that item is child of category. You may say, but I already placed that with the determinants. Well, in 99% of use cases, probably it is the same, but there are, cannot really think of a use case, but I'm pretty sure those who are using this really complex will be able to find a use case where determinants and child of is not exactly the same. So you do need to use both. If I then have this and I query it, what I'm going to see is that my hierarchy contains these 4 columns, and they are the 4 columns that I've defined in the attributes. So they are columns that stem from my dimension table. Then in red, these columns are generated virtual columns. And when I select from it, I will then see that, okay, I have in my table, for example, this row, item 230, bikini, in category 2 for the beach. So for this row in the dimension table, the member name will then be bikini, because I specified in my attribute dimension that column item name is to be used as member name. Then it has the member unique name, which is the level and the key of that level. This is sort of similar to some MDX-like syntax, so it should be familiar if you've worked with cubes. Caption and description, I'll come to at the end, time permitting. It also says, okay, for this row, the level is item, hierarchical order I'll get to, and depth is leaf. And it also shows the parent. Now, there'll then be a generated row when I select from it. And that generated row has then nulls in the item ID and name. And the category ID will be 2 and for the beach. So this row in the output has a level name category. And its parent is then all. Similar, we can have an item in another category, bobsled and winter sports. There'll be a category row winter sports, and on top there'll be this row with all items. So if we look at this and we do a select from our hierarchy, we order it by this hierarchy order, and we use the depth and is leaf, member name, member unique name in the query. We get an output here where hierarchical order is one that you'll typically use for ordering when querying these analytic views and hierarchies. And these stem from the table, and the other rows are then generated rows. We had another attribute dimension for the customers where we had the multiple branches. And for that, we just create multiple hierarchies. So we make a customer group hierarchy where we say the customer is a child of cost group. We also can make then the customer state country hierarchy, saying that customer is child of state, which is child of country. And both of these hierarchies we can then query if we want. Similar for our time dimension, date, month, quarter, year hierarchy. Day is child of month, is child of quarter, is child of year. And we also have the day is child of month of year, is child of season. two first object view types we have created, then on to the analytic view itself. That's where the fun really begins, because that's where we can make really advanced stuff, particularly in the measures. Analytic view is, of course, like all of these, just metadata, and we base it on the fact table plus attribute dimensions and hierarchies. So say we have this fact table, which has some sales per sales date, item ID, and customer ID, and specifies the quantity that was sold, the amount it was sold for, and the cost. How much did it cost us, those items we sold? And create an analytic view, create or replace using sales fact, pretty standard. Then we have two major parts, the dimension by, containing some dimension clauses I'll show in a minute, and the measures containing a set of measure clauses I'll also be showing. The defaults are not so much used for SQL, but are again more used for tools where if you drag and drop this cube onto a tool, it'll start by the amount measure. Default aggregate will be relevant for SQL. I'll get to that. And the default aggregate is normally sum. So let's look at the dimension clauses. So within those dimension by parentheses, we can put like this, where I have defined that this analytic view uses my three attribute dimensions. And with the key sales date, that's from my fact table, references date ID that's in my dimension attribute. So here I'm actually specifying like a foreign key. I have to do it here, no matter if there is a foreign key on the table or not. It's a good idea to have the foreign key on the table, but you don't have to. But here I have to specify it. Then I specify in hierarchies which of the possible hierarchies on my attribute dimensions may be used in this analytic view. And it can be that you make multiple analytic views that are using the same set of dimensions, but not necessarily all relevant for all hierarchies. And of course, it's the same for the other ones. So let's look at the measure clauses. And since I love analytic functions, the measure clauses are where I think it's really fun. But before I get into those, let's look at some simple measures in the measure clause. Simple, I have the fact. If I specify a measure, I'm giving the measure a name here, and then I'm saying it's a fact and it's quantity, which is then simply the column from our fact table. And the same with the other two. But here I have fact quantity again. Now I'm specifying an alternate aggregate. So that means that the measure max quantity, if I'm querying data on a month level, for example, my quantity measure will show sum of quantity for that month because my default aggregate was sum. But my max quantity will show the maximum quantity of that month. If it's on a yearly level, then it'll be per year, but it's still which aggregate is used. So I can thereby have multiple fact measures based on the same column of my fact table. When I have my fact measures, I go to the calculated measures, specified by as. And in those, I can use all of my other measures. So I have profit, amount minus cost. Then I have piece profit, where I use the profit I just defined up here and divide it by quantity. I have the margin, so on. I can have some calculations, any kind of SQL formula that I want to put in there. Besides the simple, lead and lag. Lead and lag are analytical functions as we know them, except that we do a bit different in the over clause. Instead of the standard over clause, we put in hierarchy and offset 1. So this means that the measure I'm calling amount prior period, it will be lag amount, so it will be 1 before, but within this hierarchy. And that'll then be depending on what level I am querying. If I am querying on a monthly level, it will be offset 1, so it'll be the prior month. If I am querying on a year level, amount prior period will contain the prior year. So that's nice that I don't have to make amount prior year, amount prior quarter, and so on. By specifying the hierarchy in the over clause, it's all taken care of for me. Lead can do the same thing, of course. In both cases, we can do it a bit different. We can say hierarchy offset 1 the same as we did before, but we can also say across ancestor at level quarter. So this means that I'm not getting, if I'm querying at date level, I'm not getting prior date. I am getting prior quarter in this measure always, no matter if I'm querying at date, month, or quarter level. If I'm querying it at year level, it doesn't make sense, and I'll get a null back. One of the things that you very often do in such calculations is you want to have a difference to a prior period. Of course, you can do that easily by saying amount minus lag amount. But since it's used so very often, they've created a couple of shortcut functions, lag diff and lag diff %, which is quite nice that you don't have to make complex calculations all the time. Well, not complex, but have to do the same calculation all over again. The window, when we put analytic functions in the analytic view, have also some bit different syntax. So we can make, for example, here a cost year to date. So that's the sum of cost over specifying the hierarchy. Then we state between unbounded preceding and current member, not current row. and within ancestor at level year. So that means if I'm querying at a specific date, it will go up to ancestor month, quarter, until it gets the ancestor at level year. And that'll be the window then. And I'm specifying unbounded preceding to the current member. So therefore I get year to date. If I'm querying at a month level, then that'll be the end date of that month, go to the quarter, go to the year again, and so on. Within ancestor at level, I could also do it at a quarter, so that gives me a cost quarter to date. We have a function, an expression called qualify. And with the qualify, we can make really complex things. Partly with the qualify, it enables us to make measures where we say, okay, this measure we call margin 2014. And that qualification says, okay, it's the measure margin, but qualified to specifically be where the date, month, year hierarchy is year 2014. So no matter if when I query the analytic view, measure margin 2014 will always give me the margin for 2014, no matter what actual member I'm querying. And I can do that with an expression to give me the differences between the margin in 2015 and 2014. So qualify can also do a pretty nifty little thing, hierarchical lag, current member offset 1. This can give me the cost year to date in prior year. So given that cost year to date is, I'm querying, for example, a date in 2015, cost year to date will then give me the sum of that 2015 up to that date. This measure will then be, okay, I have a date, go up to month, go up to quarter, go up to year. Then at that level year, I go offset 1, hierarchical lag. So I go to the previous year, and then I go back and find the same date. So it'll be year to date on the same date the previous year. That's something that could become quite involved to create a normal analytic function, but here just a bit of declaration, and it's all taken care of for us. One thing to note is that those two up there with hard-coded references in the qualify expression. It worked fine when I created these slides in version 12.2. In 18C and newer, these two don't work. There has been introduced a new bug. Connor MacDonald has made an SR. We'll see. Perhaps we're lucky in version 21 or something like that. Right, another useful little helper function that could be created differently, but is very nice, is share of. So I can create a measure profit share of geographical parent, meaning I'm saying here this share of is the profit share of the parent within this hierarchy, meaning I query on a customer-based, and then I'll get what's the profit share for that customer out of the total profit for the state. If I'm querying on the state level, I'll get the share of profit out of the total share for that country. If I'm querying on the country, it'll get me a share of profit for the country out of the total of all customers. That's with the parent. I can do it also on a specific level, saying I want what's the profit share out of the category, no matter on which level I'm querying. So share of, another nice little function that has been introduced for this. So I've now set up a lot of measures on my analytic views. I've set up the attribute dimensions. I've set up the hierarchies. It's time to start using them. Much of the added syntax, particularly all the added analytic syntax, we have used those within the analytic view definitions. And we have that the hierarchies have some member names so that we can query somewhat MDX-like. And what we do with this is to use a select clause where we, in the from, put the analytic view instead of a table. And then we can use all these measures and the columns of the hierarchies as normal column expressions. So as an example, we have the sales analytic view we have created before. We put it in the from, we state hierarchies, and state which hierarchy we are going to use here. This is then similar, that behind the scenes will happen a join between our sales facts and the date time dimension table. And then all of the measures we are querying here, they'll be created analytics equal to get that data out of those tables. What I'm doing here is that I'm querying on the level name equals month. And I'm then querying various of the measures. So the output of this gives me 48 rows. I have data from 2014 to 2017. And I have some amount prior period, for example, that we can see is retrieved from up here. But I didn't have to write lag in my query here. That lag was already defined in my analytic view. So like normal views also can hide some complexity of SQL, all of the complexities here is hidden inside the analytic view. And the one who uses the analytic view doesn't even have to worry about analytic functions. That means on your development team, you can have the heavy-duty people create the analytic functions, and then a whole lot of other people can just write more simple SQL querying on these. Say another example is that we query specifically on those where the parent is year 2015. That'll be the 4 quarters of that one. And we get output here with those 4 quarters. But notice that even though our where clause stated we wanted to see those with those parents, amount prior period up here is still filled, because with the quarter 2014 Q4, it's not like regular analytic functions that we have first filtered the data to 2015. Then when we do lag, it's too late. We cannot get 2014 data. Here, it looks also back to the previous year's data, because that's how a normal cube would work, and think of this as a virtual cube. Same with our year-to-date prior year. We have here data from 2014. Yet another example where we show how we can work with all these generated columns in the hierarchies. We can, for example, say we want that the year ID should be 2015 of that hierarchy. The year ID will be 2015 both for years, quarters, months, and dates within 2015. But then we specify is leaf to be 0. So we don't want the lowest level, that's the dates. We want just the quarters and months. And the all, of course. We have the all. Sorry, we have the year level, not the all. The year level, the quarter level, and the month level. And the thing then to note, as I explained earlier, our quarter to date, for example, here, the quarter to date, okay, for the month of January, then we have a rolling sum here, February, rolling sum here. And on the quarter level, of course, it is just that quarter. On the year level, quarter to date doesn't make sense, so we get a null. Yet another query example where we state we just want the level year, and we get all 4 years. In this case, amount next, here we do get null because we simply don't have any data for 2018. We can use more hierarchies than one if we want. So we have here both item category and date, month, season. Here we use it so that we query on the date, month, season, and we query specifically for the summer. And what we want output is per the item category hierarchy then, and we output using the depth and members of those, and we output in that hierarchy order. So we output that, yes, as we suspected in summer, for the beach sells quite a bit more than winter sports. And note again that with these hierarchies, these is that sum. And then the 2 categories are summed in the all items. It's like a group by roll-up, but I didn't have to do anything in my query stating that I wanted to do roll-up. It just happens magically. Another query example using 2 hierarchies, customer state country and item category hierarchy, so that we can see some more data. I'm going to go quickly here with those examples since I have only about 10 minutes left. Just to show that, yes, I can also do with all three hierarchies where I query on April and I only want depth 1 and 2 for the two other hierarchies, so that I get an output here which is similar to a group by cube. That gives me all the combinations of item categories and countries. In 18C, there's been added that when I query the analytic view, instead of just doing from sales AV, I do from analytic view, parenthesis, and then stating using what I had before, the sales analytic view and the hierarchies, but then I can modify. Here I'm doing a filter fact, and the filter fact states that I want it to filter away some data from my fact table before it starts to apply all of the calculations. So I'm filtering out Q2 of 2015. That means that now I have a null here in the amount prior period. If I had just done this in the where clause, I would still have seen amount prior period being data from Q2, but filter fact filters away the facts before applying measures, calculations. Filter facts here in a different way. I'm filtering out all Q2s, which also then influences my cost year to date, including the one in prior years. I can do another thing besides filter fact. I can also add measures. So I can add extra measure formulas for just this query, besides those that are already defined inside the analytic view. So here I'm doing, for example, cost year to date 2 years prior, where the one I had in the analytic view was just 1 year prior. So that I'm getting cost year to date prior year, and year to date prior year. So brief look at the performance. It's just SQL. It will be rewritten to ordinary SQL, so you tune it the way you'll tune basically all SQL. Work with indexes, work with index organization, work with in-memory option could be quite useful for something like this. Or one of the things really useful is that you pre-aggregate some of the levels with materialized views, and then query rewrite can kick in and get the data from the materialized views. So to show you what it means that it's just a rewrite, here is a fairly simple little query with the analytic view. If I use expand SQL text, this is what it looks like. And you can see that it's utilizing that we can now have long identifiers, date, attribute, dimension, hash, date, month, quarter, year, hierarchy, hash, member name. They really use that you can have long names. Notice also dot, it goes on and on and on. That's actually about 8 megabytes of SQL. 8 megabytes in 12.2. They've done some optimizations. 19C, it's 1.5 megabyte, not so large. As I said, the query rewrite on using materialized views, it's very useful. There's a bit extra you can do when you have created materialized views. You have to look up in the documentation, they have to be created containing specific columns and specific group bys in order to be useful for this. But then when you do that, you can use the syntax cache and state some levels where you then tell the database, I have created materialized views for these levels. And that will then mean that the generator that generates the SQL can take that into account and generate SQL that will use the materialized views directly. That can be a better, at least in some cases, better and safer way than relying on normal query rewrite to kick in. As you've seen, it can be quite complex. So it's a nice thing if it can be written more optimal straight out of the box instead of first generating very complex SQL and then query rewrite has to work it back into something not quite as complex. I'm going to just go very quickly over the classifications here, just to note them. It's metadata about your metadata, and they are not used when you query with SQL. You can query them from some dictionary views that exist on these classifications, but it's meant, again, to make this look like a cube for visualization tools that access this over, for example, the OLEDB for OLAP provider. What it means is that I can give the objects captions and descriptions. I can give each level within attributes. I can give captions and descriptions. I can give captions for individual members of my dimensions, and so on. I can do captions and descriptions on hierarchies. I can do captions and descriptions on the analytic views. Basically all over, I can put captions and descriptions. There's a long syntax. Caption and description, as you see it here, is the shortcut. There's a long syntax. Classification, caption, value. Classification, description, value. And that allows you also to do classification, whatever value, where you can define your own classifications that you then use in your own dashboards, for example. There are also classifications for formatting, coloring, again meant to be used for these visualization tools. And classifications can be English, German, Danish. You can create classifications for multiple languages. So, summary, the analytic views, they allow a dimensional analysis of your data on the real-time data without copying any data to data warehouses or cubes. Also, you don't have to write the complex analytic SQL when you do the querying and analysis on your data. You write that complex SQL once in your analytic view. It's a very nice idea and quite useful, but as we saw, there's even been introduced bugs. As of now, it's not entirely mature. All of these examples like shown here works, except those that are noted as bugs. But if you do add more complexity, you can break it. So useful still, but do not expect it to be a replacement for a cube. Not yet, at least. A couple of links, a link to this presentation and a link to a script containing all of the demo code. And basically that concludes this, and that means that I should try and see if I can open the chat for questions. And I see there's one question. How long does it take to hard parse a SQL of 8 megabytes? Well, it wasn't that bad on, I think, maybe a second or so. I was, let's say, pleasantly surprised. But still, yes, hard parsing is something to take into consideration. But still, when you compare this to like data analysts that sit and do ad hoc querying, it's not, this is not typically queries that are going to be executed thousands of times a second, hopefully. Other questions? Well, in that case, I'll see if Alfredo has something more to say, and otherwise I thank you for your patience and hope that it was useful for you.
Thank you so much, Kim. We really appreciate you taking the time to present to the group today.
You're very welcome.
Awesome presentation. Yeah, the presentation was very awesome. So for those that maybe got on the call a little late, you can catch the recording on YouTube. It should be available under the Chicago Oracle Users Group page. Pretty easy to find if you search YouTube. And as I mentioned earlier, next week we have Oracle ACE Director Michelle Hardwick and Assistant Director of Business Analytics, Leonel Nieto, on dashboarding tool of choice for Apex, which should be a really awesome presentation. So hopefully we'll see you then. Same time and same day of the week, as always, Wednesday at noon CST. So hopefully we'll see you then. And thank you again. Take care.
Enjoy the rest of your day.